Okay, in this video, we're going to continue on with some concepts of probability and then add on to our formulas that we've been using. So if you roll a die, we talked about there are 6 possible outcomes. Each outcome is equally likely, so the probability of rolling any number is 1 out of 6, or 1/6 chance. So remember that top number represents the possibility of getting, like, say, a 2 or a 3 or something like that, right? It's not actually, we're going to put the number that's on the die in there. We're just saying, what's the possible out of 6 faces? There would be one face that's a 2, so that's the possibility of what we're going to get. So we want to think about, like, what if we had other numbers involved? What is the probability of getting a 1 or a 6? And we talked before when we did set theory about or being and or. So that could be getting one or the other or both. So in probability, we talk about favorable outcomes, or we may call them successes. So the outcomes we are interested in, getting a 1 or a 6, are called favorable outcomes or successes. So even if it's something kind of that might have a negative connotation to it, we still call it favorable or success, because that's like the event that we're interested in. So that's kind of a weird little thing to think about as you're doing these. Of the 6 outcomes, 2 are favorable. So the probability is 2 possibilities, the 1 and the 6 added together, the amounts of those, the cardinality of that, then we reduce it to 1/3. So 2 out of 6 is 1/3. Now, because we don't have any overlap, any intersection, we don't need to worry about subtracting that off for our union in this case. Okay, and again, favorable or successes, we mean to the event in question happening, like that actual thing happened, or the possibility that we're looking at of that thing happening. So if we were doing an experiment per se, and we did a bunch of rolls, we would be looking at how many times did a 1 come up, or how many times did a 6 come up, and we add all that together, divide by the total number of rolls that we did. So the more we roll and the more trials that we have, will approach the theoretical probability, just like we talked about before. So this is called the law of large numbers. It states that as the number of repetitions of an experiment is increased, the relative frequency, remember relative frequency is we take the number, divide by the total, obtained in the experiment tends to become closer and closer to the theoretical probability. So theoretical is the ideal world. We're doing, what are the possibilities? We're figuring out the sample spaces by tree diagrams or charts and things like that. Where experiments or empirical, we are actually doing an experiment or trials that we are just like actually rolling the dice or flipping coins and things like that. If you spin a spinner with blue, red, yellow, and green sections that are equal sizes, then what is the theoretical probability of the spinner landing on red? So think about that. We would have 1 chunk of red out of 4 possibilities. So that would be 1/4. So that would be our theoretical. So now let's see if we do a simulation and how that works out. So I have a link here that you could copy and paste, or you could just follow along as I do it. But if you want to try it, this will be in your note sheet. So I'm going to go ahead and click on this website and switch over to that screen. This is really bright compared to what you've been looking at, but here's our Interactivate website by Showdoor. We have a spinner here, and I had to click to get the 4-piece spinner. And I have these different colors, so if it's hard to see colors, then we have blue in the upper left, then the red to the right, upper right quarter. Lower right quarter is a bright green, and lower left quarter is a bright yellow. So you want to click here and do number of spins at a time. We can kind of increase that. I'll do 1 at first, and it's going to create a little tally next to your blocks over here on the right. We have red, blue, yellow, green down the line. So then you click here and you do a spin, and it landed on blue. So here's your 1 tick mark, and then totals over here. So it's kind of cool. Then you just keep going on. And I'm getting a 1 for red, a 2 for red. And so far, it's all about red and blue. Now I've got 1 green, so I have 2 red, 3 blue, 1 green. Keep going and going and going. I'm just going to click a bunch. So you can see it's not quite even like you would expect, like 1/4 if I were to reduce those fractions and get 25% for each one yet. But as I do more and more, it should approach that. So if I were looking at, I think it was red we were talking about, 2/8, that actually does come out to 1/4. The blue isn't though, and the yellow isn't. I can just do some more spinning. You can see like the others are increasing, but the yellow is still only 1/10. So that's pretty low. So let's see if yellow can catch up with the others. It should be equally likely in the long run. So I'm going to click like 5 spins at a time. I'm going to get it to going quicker. So it'll simulate as if we did 5. So it's going to drastically increase. And you can see now that the yellow is catching up. If I do 10 spins at a time, so it's magically doing 10 spins, tracking it all in the program, and then plop, there's your 10 trials. So now the blue and yellow are behind, but law of large numbers tells us as we do this, more and more it will approach. So I'll do 1 more spin here. You can see what it comes out. And so we were looking at red, I believe. So 13 out of 45. So let's just see what that comes out to be. And that is 0.2888, so on and so forth. So we would say 0.289 is what we would round to. We usually go to the nearest tenth of a percent. So that would be 28.9%. And we're looking at the ideal or the theoretical as being 25%. So it's getting there. So hopefully you get the idea with the more and more trials. So we really want to have, when we're doing our data sets, we want to try for at least 30 trials or 30 people that fill out a survey and things like that. However, you know, in class, we have a smaller class, or online even, they're probably around 30 or a little more. So we're dealing with small data sets. So you'll notice when I give you data, I'll combine all the classes together. And on this website, there's different kinds of things like the dice, like you could do the sum of the dice and get a data set that way. So it's just kind of fun to play around with, and there's all sorts of different interactive things. So we might use these in some of the activities. All right, so let's go back to our notes. Now we're just going to look at a couple of other types of scenarios. We have cards, the same formula goes. Probability of drawing an ace. We would have 4 aces in a deck out of 52 total cards. Reduce it down to be 1/13. Now you might want to wait to reduce till after you're done working with all the problems, but your final answer should be reduced fractions for this case. Sometimes we do convert to decimal, but for these types of small fractions that are we're using for cards and dice and coins, we typically leave it as fraction. Another one here would be draw a club. Probability of that is 13 clubs out of 52 in a deck is 1/4 reduced. Okay, here's another example. Say you have a bag of 20 cherries. 14 are sour and 6 are sweet. So if you pick a cherry at random, what would your probability be for sweet? So we would have 6 sweet out of the total 20. So that would be 6 out of the 20. And we would get 0.3. Or 3/10, 0.3. A lot of times we can round as long as they terminate. And we would just say 30%. So what if we said our event now is sour? What would the probability of that one be? So go ahead and try that. Okay, good. That would be 14 out of 20, or 7/10, or 0.7. Or we could say 70% likelihood. So do you think that's really accurate with these, though? Is it the same kind of thing as all things being equal, like with a die or coin or the cards? Okay, remember, they need to be legit things, all the same chance of getting picked. So with this one, take a minute to think about that and jot down some issues, or if you think it's all good, write that too. Well, we'd have to know a little bit more about cherries maybe and explore. So we've got to consider the size. So here's the sour cherries and the sweet cherries. So the sour are smaller and the sweet are larger. So you would be more likely to grab the larger sweet cherries. So even though we said the sweet cherries, I think we said 30%, right? Probably we're going to get more picks on that just because they're more likely to be grabbed. So that wouldn't be a good chance of a likelihood. Or we just want to consider that. Like, okay, well, if they're bigger, I want to put that in there. Like those slips of paper you put in for raffles or whatever, or you put your name on them. If you leave them big, that's better. Or sometimes people like to bend them a little so they'll get grabbed better. So just some things to think about. Okay, next we're going to look at different sample space. 2 dice that sum to 6. So we you probably have seen this in the set theory videos, but just in case, just to remind you, we have a die chart to get the sums. So 1 plus 1 is 2, 1 plus 2 is 3. So all the totals are here in this column. And we can see that we have 6 occurring, a sum of 6, 1, 2, 3, 4, 5 times. So you throw 2 dice. What is the probability that the sum of the 2 dice will be 6? So we would have our 5 occurrences of 6, and the total possibilities, we would add up our totals to be 36 sums. Okay, so here's all our possibilities divided by our total. So go ahead and just do the math on that. You can pause or just do it really quick, jot it down. Okay, answer would be 5 out of 36. Okay, now we're going to look at or and situations. So our union and our intersection. Okay, as you may recall from the set lessons, we have or being the union. We use this symbol, it looks like an upside down U here, horseshoe. An outcome is in the event A or B if the outcome is in A or it's in B, or it's in both A and B. So sometimes we won't have any kind of intersection at all, and that would just be 0. But if we do have an intersection, we don't want to count it twice, so we would need to subtract that off. So if we have A, our event A is 1, or the set with 1, 2, 3, 4, and 5, and B is a set. Remember, these braces mean set 4, 5, 6, 7, and 8. What do you think is in the union of A union B? So go ahead and jot that down. Find A union B. Okay, so right now we're just reviewing our set theory, not getting the probability yet, but we need to know how to count these things up. So refresh on that. So A union B would be everything in both entire sets, except we're not going to double dip. So we have 1, 2, 3, 4, 5, 6, 7, 8, and we're only going to list that 4, the shared number or element, 4, and the other shared element is 5. We're only going to list that once. So that's kind of like by looking at it, or you could do a Venn diagram with it, or you could list everything out and then subtract off the shared items, the intersection. Especially if you're just doing the cardinality of it and looking at the numbers, not actually what's in the set. So if we have and, that's an upside down horseshoe intersection. An outcome is in the event A and B if the outcome is both in both A and B at the same time. So in this case, we already kind of talked about that. What is the intersection? Let's go ahead and jot that down and set notation. Okay, and that would be A intersect B, written like this, with the A upside down horseshoe, B equals the braces 4, 5, and brace. Okay, a couple more for this section here. Complement. The complement of an event A is denoted A prime, or sometimes it has a little c, or you say A complement. consists of all outcomes that are not in A. Okay, so keep in mind that your probabilities all need to add up to 1. So if you're thinking about if you have the probability of an event and you add the probability of its complement, you would get 1 or 100%. So just keep that in mind. So for example, if we have the set S equals 1, 2, 3, 4, 5, and 6, and let A equal 1, 2, 3, 4, then A complement would be 5 and 6 because those aren't in A. So what is the probability of getting A? How would we figure that out? Because we can see what's in this set, but we really just need to count the cardinality of it and make sure, again, we don't put the numbers that are like the names of the actual elements or outcomes. We want to put just the amount. So if I have A complement, I have 2, but A has 1, 2, 3, 4. So if I'm asking for a probability of A first, go ahead and jot that down. Okay, so that would be 4 out of 6, or 2/3 if we're talking about a final answer. But then if I were to say what's the complement, you could just figure out, well, 1 subtract 4, 6, or 6, 6 minus 4, 6 would equal 2, 6. Then you could figure it out that way. Or you could just count up, there's 2 elements out of 6, and I would have 1/3. So here's the math on that. 4, 6 equals 2/3. Once I get that, I really don't need to even do any division for the complement because I can just do 1 minus 2/3 is 1/3. If I had more complexity with it, I might want to just keep my larger common denominator and then reduce at the end. This one worked out nicely. And remember, our probabilities should add up to 1. Okay, next we're going to look at conditional probability. In conditional probability, we are looking at event A, but if, when, or given the condition B happens, we write that as P parentheses A, the line, B, and parentheses. That is the probability that event A will occur given that the event B has already occurred. So it's a condition placed upon it. And we'll look at that when we do the example. The conditional reduces the sample space. We calculate the probability of A from the reduced sample space B. And there's a formula to calculate this. We take the intersection of A and B, probability of A and B, and divide by probability of B, which is the condition, and we have to make sure that's greater than 0. For example, suppose we toss one fair 6-sided die. Find the sample space. So take a minute to write that out. We would get 1, 2, 3, 4, 5, 6, and we notate that as capital S. If we let A be the event rolling a 2 or a 3, we have 2 elements in that, and let B equal an even number in that set, 2, 4, 6, we'd have 3 elements in that. Find the probability of A given B. So first we're going to look at the formula method. And remember that S has the 6 outcomes here. So using the formula, and you could try this on your own, we would have A given B, probability of A intersect B. We have one shared element from A and B out of 6 for the total sample space. So in this case, using the formula, we're going to look at the total sample space. And then we would divide that, but just leave it as 1/6. Then we have the probability of B would be 3 elements out of 6. And you can notice here, if we were to reduce this down, we would get 1 out of 3. So I'll just show you quick how we would divide those out. The 6 will reduce out and leave us with 1/3. Now, sometimes we have to use the formula. We just can't work around that, and depending what we're given or how we're doing the problem, we're going to use this formula. We might just be given probabilities, just the percentages or whatever. But we can also kind of do the intuitive method here. And notice we get the same result if we just say, okay, we have intersection 2, what's in A, and B is the 2, and divide that by the number of elements in B, and we could just jump right to the 1/3. So a couple of different ways to do it. Kind of like when you were doing, union, you could use a formula, or you could use a Venn diagram and do more of the intuitive method. So same kind of idea. Okay, so now we're going to look at a more complicated example, or actually a try it. So here's a bunch of problems for you to do. So pause the video and fill this all out. You're going to start with the sample space S is the whole numbers starting at 1 and less than 20. So go ahead and list those out. So we really want to see what's in the set. So use the braces and list it out. And remember that it's up to 20, but not including 20. Then we have event A is the even numbers, and event B are the numbers greater than 13. So list those out here in line B. Then we're going to find the probability of A, probability of B. We'll look at the intersection of A and B, the union of A or B. For line E, we'll have probability of A intersect B, probability of A union B. Then we'll find the complement of A, probability of the complement, and then what do those add up to? We know it's supposed to be 1, but make sure it actually is 1. That's one way you could tell you've done it correctly. Then you're going to look at the probability of A given B, and the probability of B given A, and then are those the same thing? And if they are, would that always be true, or maybe they're not? And we've already proven it false. All right, so pause the video and work on those, and then I'll reveal the answers shortly. So check it against what I put up. Okay, so hopefully you've paused and done that. If you haven't, you may do so now, and I am going to reveal the answers. If you're stuck, that's okay. We'll kind of look through it together. So here are the answers. So set would be 1, 2, so on and so forth, all the way up to 19. So there's 19 elements. A would be 2, 4, 6, 8, up through 18. B is greater than 13, right? So we have 14 up through 19, but it includes the odds, not just the evens. Now we look at the probability of A happening. That would be 9 out of 19. We can just leave it as a fraction. Probability of B is 6 elements. out of 19, so 6/19. In the intersection, we can look at the sets and see, it's probably easiest to just look at B and find the even numbers in B, 14, 16, 18. For the union, we want what's in both entire sets, but not having the overlap. So you're gonna only count that 14, 16, 18 one time. You list it out, you wouldn't double list. So we have 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18, 19. For A intersect B, we would have 3 out of the total. Remember, our total is 19 for set S, the sample space. 3/19. For the union, we end up with 12 elements out of 19, 12/19. The complement of A would be all the odds. So we're listing those out. I should have braces around here. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. Probability of that is 10/19. They add up to 1. Probability of A given B, we would have 3 elements in set A intersect B. Remember, if we're thinking about what's in going by the formula. And then we would have 6 in B, reduces to 1/2. And then we have B given A is 3 out of 9, so that's 1/3. So the probabilities are not equal. And you could do the long way around with the formula. You could do 3/19 over 6/19, and then the 19ths would reduce out and you'd get 3/6. So that's it for 3.1. Hopefully that helps you be able to work through your homework and understand more about what the probabilities are, how we use those sets, all the things you're familiar with set theory, and now you're applying it to probability. Have a great day. We'll look at 3.2 in the next video.